Okay, this is the next chapter, modelling. Chapter A9 is to do, we've done some of it before with proportion. It'd be useful to go over it again. Anyway, okay, so the first part is to do with distance, time graphs, etc. Okay, so I'll just go through this. So here we have, write down the time that Jamie left home. So that's here. Okay, and so that is 10. Okay, write down the distance when he was at 10:20, and so that's that point there, which is 3 squares up. So that's 6.5 kilometers. He left the house to return home. I wonder if I can do. No, okay. He left home and he came back at 11:50, which is there. And so, as he went at steady speed, it's a straight line. Okay. Now remember, the gradient on a distance time graph is the speed. Okay, so because it's distance divided by time. Okay, so the steeper something is, the faster they're going, and when you obviously have a horizontal here, it means they're not moving at all, and it's they're not going at any distance at all. Again, when you do this line here, make sure you use a ruler, otherwise you'll get marked down. This part here, work out the time Jamie spent at his friend's house. Well, that's from this point to this point, which is 30 minutes. Okay, and I've completed this part of the graph here, 11:50. I did that first. Okay, and the last question is work out the average speed. Now notice it's in kilometers per hour. So what you can do, because he goes 40 kilometers, you could do 40 kilometers divided by how long he spent there. So he left at 10. He started at 10:10 and finished at 11:50, which is 1 hour 40 minutes. Now 1 hour 40 minutes is 100 minutes. So you could do this divided by 100, but this gives you kilometers per minute. So if you want an hour, you can multiply that by 60, which gives you 0.4 times 6. 24 kilometers an hour. 24 kilometers, an hour. Or you can do 40, the direct thing, divided by 1 hour 40 minutes. Now 1 hour 40 minutes is 1 hour and 2/3 of an hour. Okay, so you could divide 40 by 1 2/3, which is 5/3, isn't it? Okay, which does give you the same value, 24. I just checked on the calculator. So either one of those is fine for kilometers per hour, but just be careful of units here. So too many people will put 1.4, especially if you're putting it for an hour here. And if you work out the minutes, you've got to multiply by 60 because it's hours. Okay, next we're going to look at this. This is actually one of the questions in the book. If I'm filling this water up, this beaker up with water, what is the graph going to look like? Well, it's going to be steady here and steady here, okay, for measuring the depth. Okay, but the depth is going to increase a lot quicker here than it is going to increase here. Okay, so we'd expect to see the depth increase at a steady rate, which is a straight line, and then increase at a steady rate but quicker. Okay, like that. Okay, steady rate, and then when it gets to the neck, it goes up like that. So here we would expect the rate to start off at a rate, but as we get wider, because it's the same amount of water coming in each time, we would expect the depth to go up slower and slower and slower. So the depth increases quickly to start off with, and it slows down as the neck gets wider. here, well, this is just a fixed diameter, and so we would expect that to go up at a steady rate. And this one is like the inverse of this, so we'd start off slowly and then we'd go up quicker and quicker and quicker, like that. Now you're expected to be able to look at graphs and look at things like this, real life situations, and be able to interpret the data that you have and be able to do some graphs like this. Okay, so let's have a look at this. Bob drives 20 miles, puts £20 of fuel in his car and drives 50 miles. How far can he drive on £38? Now this is what's called direct proportion, okay? And you could write it off as, so the fuel is proportional to the distance, miles, okay? And we're going to look at a question like that in a minute, but here most of you can work it out by doing this. 20 over 38, which is 20 mile-pounds over 38 pounds, is the same as 50, is the same ratio as 50 miles to the distance of 38. Okay, it gives what x is equal to 38 over 20 times 50. So x is 95, and we would expect that because 38 is nearly double 20 pounds, and so 95 is nearly double 50 miles. Remember, it's always useful to check your answers just to see if there's any problems. So let's have a look at proportional change. So here, this is a typical question. So ball's being dropped. The speed, the distance the ball drops is dependent on time, and it's directly proportional to the square of t. So what they mean by that is t squared. Okay, so like I did before here, we've got this proportional. Here, d is proportional to t squared. Okay, and that's how we'd write it. And so I can write this always, I can write this as, because it's a direct proportion, when this value is 0, this value is 0, this value is 0. And so it has some proportional constant. Okay, so I can say that d is equal to some proportional constant, which we call k, times this t squared. This is always true, so no matter what they say about what it's proportional to, or directly or inversely proportional to, you can always write it as one of the variables is equal to this constant of proportional times whatever the thing is. So here we've got squared, it could be cubed. If it's inverse, we'll look at that because that's on the next slide. So it gives you here it gives you here what they are to start off with. So it says that if t is 2, d is 20, and so it will give you, that tells you what k is. So if t is 2, that gives you 4, and 20 divided by 4 is clearly 5.